welcome to the first talk of KUIS AI Talks in 2025 fall semester. We are very happy to have Jiazhi Yang with us. Jiazhi is a second-year Ph.D. student, which is hard to believe, by the way, considering the amount of work he has done at the CUHK University. And we know him through Hongyang, our long-term collaborator at OpenDriveLab. And we have been collaborating with Jiazhi in the last year, and it was super fun. He was an intern at OpenDriveLab. He works on building generalizable models for embedded intelligence. And he is the first author of recent NeurIPS spotlight paper, ReSim, as well as a co-author in very influential works in self-driving in the past few years, like UniAD, which won the Best Paper Award at CVPR 2023, GenAD, which was a CVPR 2024 highlight. I don't know why he didn't list Vista. You are an author on Vista as well, Jiazhi, right? Vista,
yeah.
Quite influential work. I think NeurIPS 2024, right?
Yeah, it's 2024 NeurIPS, yes.
So he is like, despite being super young and just like second-year PhD student, he has done quite influential work, and we are very happy to have you here, Jiazhi. Thank you very much for accepting our invitation in the last minute, kind of. So we are looking forward to his talk on pathways of igniting world models for intelligent autonomy. Stage is yours, Jiazhi.
Thank you. Thank Professor for a nice introduction. And I'm so fortunate to have the opportunity here to introduce my recent line of work. So my research focus for the last 2 years is all about developing a world model for intelligent autonomy. So for previous 3 works, it's basically on autonomous driving specifically, and right now I'm also doing a bit of research into the robotics regime. I will do some minor touches on that in the end of this presentation. Yeah. So I'll mainly focus on these 3 papers. Yeah, and to start off, I might introduce some basics concept about the world models, the progress and the challenges. And after that, I will introduce my most recent work, ReSim, which is accepted at NeurIPS 2025 as a spotlight paper. And after that, I will share my personal perspectives on the directions and methodologies to push forward this method, or push forward this direction of world models even further to make it more applicable to our real-world applications. Yeah, so the motivation of developing a world model is actually learning an abstraction of the realistic world. So the world model is basically an abstraction of an environment that predicts future states based on the observation and the action proposals. Yeah, so it functions just like the actual physical world, but it's instead a neural network. And the world models is proven effective in various domains and regimes, including gameplay, such as the Dreamer Victory series, and the real-world robots. Sorry, it just popped up. And the real-world robots, such as the UniSim, which has got the clear Best Paper Award for the last year, I guess. And also the navigation, which is the navigation world model that's conducted by Professor Yangin. Yeah. And despite that, we didn't see a proper world model that's specifically used for autonomous driving. So our vision is to develop such a world model that has so many good features we want by utilizing the worldwide driving data in training. And after that, we can have realistic real-world dynamics and minimal visual gaps because it's mimicking the real-world observations, right? and a good scenario generalization since it's pre-trained on a large scale, wide scope of data. And then it can actually improve the decision making. So yeah, so my last 3 research work is all about developing such a driving world model at scale. And sorry, let me squeeze it a little bit. Okay. So the first work, which is accepted at CVPR 2024, is about proposing a large-scale data to support the training of such a large neural network. Because at that time, we cannot find a validated data to do such a large-scale training. At that time, we don't have something like the Waymo nuisance, which is about 2 hours, 4 hours, less than 10 hours of horizon of the total horizon. So it's pretty limited scale, and we want to enlarge it. So our idea is to get such data from the web. So we gathered more than 1,000 hours of driving videos, the raw videos that's recorded by the drivers around the globe. It covers more than 244 cities around the globe, and we gather such data mostly from the YouTube sources. So it's a pretty diverse data set. And with such data, we can then do some pre-training. Yeah, but after that, in recent days, there are data set that's at more larger scale than this work. But at that time, we don't see this data set coming out, so we develop it on our own. And we are probably the first work to pre-train our model with the video prediction objective. So if you can think about that, most generative work are doing things like text to video generation. Like the condition is not a video sequence or an image or an observation, it's a text. But the text is not grounded to the physical world. So back in 2024, we are probably the one of the first groups to decide to use the video prediction that's conditioned on a sequence of observations instead of a text or instead of a human attention to do the training. And the objective is quite simple. It's just predict the next few frames based on the observed frames. Yeah, with the diffusion architecture. And after that, we realized that a proper world model should reflect the consequences of applying an action, right? But such action label is not existed in the unlabeled YouTube data, because YouTube data is just raw videos without any annotation. So there are no segmentation maps, there are no vehicle trajectories, no waypoints, no control signals. There's nothing. But if we want to do a world model that can tell the consequences given any given arbitrary action proposals you want to take, it has to be trained on a data set with the action labels, right? It has to train the data set with the pairs of data, such as a video sequence associated with a corresponding action sequence. But we just don't have that. And if we want to do that properly, we might have to connect a large scale of data on our own. But as a researcher, as an academia researcher, we don't have that resources to gather such large scale of data with action labels. So we have to figure out other alternatives to approach this. So we devised an effective co-training strategy that it's simple as just co-train your word model on both unlabeled data without any action labels and a small scale of labeled data such as nuisance. You compose them together into the training, and the model can generalize to a larger distribution beyond the narrow targeted nuisance data set. Yeah, so to be more specific, we only train the action condition data with the nuisance examples, nuisance samples, right? But we can, after training, we can generalize such a action controllability on any given images or any given video sequences. And also to be compatible with multimodal actions. For example, the high-level command, the goal point, and the trajectory. We developed a unified conditioning scheme that just project any kind of action types into a high-level dimension feature. And then you can inject the feature into a diffusion model, and the diffusion model can be controlled by any one of these control representations. Yeah, so once we got here, we ask ourselves, are these models good enough since they can be controlled in a wide range of domains, scenarios, right? And the answer is actually not. To illustrate this, we can see this figure right here on the right. So if we train our model following the Vista plan, and we want to control this video with a suboptimal action, such as given this past three images, we want to control the vehicles to turn left. And we can see that the word model cannot simulate the corresponding future sequences based on your suboptimal actions. So if it's a proper word model, if it's a good word model that can reflect your action, it should have the imagination of turning left and maybe crash into the wall. But that's not the case for any previous word models. And the reason for that is such a philosophy of developing such word models is quite biased. They are biased towards the normal action. So if you think about that, things we are controlling our word models with only the human demonstration actions during training, right? So we are using a high quality, small scale data set, nuisance, as the action condition samples. So their action labels are actually conducted by human drivers. And these actions are mostly safe and high quality and will not lead to any negative consequences. Yeah, because it's human driven. So if we train the model on such corpus and you want to inference the model on negative consequences or suboptimal actions, it cannot follow what you want. It will still try to find the safe way to go through this tree. It will not follow your prompt to turn left or turn right. And the question is then, since we know that how to gather such data with a wide range of actions, right? As we know that for any real-world corpus, any real-world driving corpus, we cannot get such a diverse range of actions for each state. We can usually just get a pretty safe human demonstration actions. Yeah, so this leads to my latest research. How to reliably simulate future driving scenarios under a wide range of ego behaviors. Yes, so the idea is actually quite simple and straightforward. As we can see, the real-world data, any type of real-world data, are mostly composed of expert actions. If we want to, or we want to gather the non-expert actions or suboptimal data, we can only find such data in simulated regime. So to do so, we have to try to utilize the simulator to synthesize a wide range of different ego behaviors and use that to complement for the training corpus during the training of the word model. since the simulation is not physical world, you can basically do what you want. You can basically just control your ego vehicle in any type of ways. So the action distribution is extremely diverse. So you can freely crash into any scenarios, any object, or flexibly interact with any agent in the scenario. And the recorded action is far diverse than the real world corpus. But here comes the question. So as we all know, the simulated data has inferior visuals, right? So the vision quality is not as good as how the real world looks like. So can we simply just utilize this into the co-training and make the best of both worlds? And our answer is actually yes. So due to the compositional generalization of large-scale diffusion models, if you train such different domains despite their gaps in visual quality, or despite their visual gaps, we can still just compose these different two corpus into the world model training. And after joint training, we can successfully transfer the length dynamics from the simulation into real-world scenarios. So after the co-training, we can more flexibly control our ego vehicles to do the expected behaviors. And also, to highlight this part, we have not seen any of these consequences in real-world corpus, but it can generalize to real-world conditions after the co-training, right? We cannot see such a scenarios of crashing into or turned into the side of the work in real-world corpus such as ReSim and OpenDV, but we can generalize to this thanks to the large-scale co-training. Yes, and the model architecture is quite simple. It's basically a large-scale diffusion, a video diffusion network. And we condition this model with the history observations and a high-level prompt indicate the direction to go to, and a low-level trajectory encoder. So it encodes the intention of your actions. For example, you want to turn left or turn right. That action, you control that as the input. And with this given inputs, the model will go through the diffusion process to produce the next 4 seconds of video sequences. And to encourage the dynamics modeling, so the dynamics modeling means that to encourage the temporal coherence across the video frames, we devise a dynamics modeling loss to improve the coherence in the temporal horizon. So the basic diffusion loss is pixel-wise, so it does not introduce any prior on the video level. So we devise it to make it more smooth and more reasonable in the temporal dimension. And we another interesting and another trick we find out quite useful is that during training, we add more noise, we add higher corruption into the training process to encourage the model to find the high-level structures. So it's basically tell the model to first learning how the structure of the environment should be instead of focusing on the each pixel. So it's like the background, like the trees and the sky. So instead of modeling this, we want to model high level the structure of the scenarios. So craft your training, craft your conditions during the training process is actually quite useful in our setting. And the optimization stage are composed of three stages. And And to highlight that, we mostly find the most useful part is the second stage. That is to learning the action controllability on a low resolution. So which is also used by my last paper, Vista. So it's quite useful. So if you directly inject the action signal into a general purpose video diffusion model, which is not used for action controlling, you will see that the learning is quite ineffective. It's hard to learn to control your word model despite the long training time. But with a low resolution, you will see a much effective learning of how to of controlling your word model with the input, newly introduced action input. So it's an extremely important trick, I think. And yeah, in total, we trained this model with 2 weeks. Yeah, with 40 GPUs. And here are some visual comparisons to demonstrate the importance of co-training. So the first 2 columns are alternatives of our proposed models with the simulated data and without the simulated data. So both models include the real world data in training, right? But the left side, we also have the simulated data with a wide range of actions during training. And on the right side, we don't have the simulated data. We can see that by introduce the simulated data during training, and you can more flexibly and more accurately control your ego behavior. So here, the given action proposal is sort of turning right. Without the simulated data, it cannot run into the grass, right? Because because the model has never seen such running into the grass scenarios in human demonstrations, and it might see some of these samples in simulation. So that's what the benefit of the simulated data. And on the third column is Vista. Basically, it's just worse than any of the first 2 columns, right? And our model can also simulate some crash scenarios, despite it has never seen any crash scenarios in real-world corpus. So for the second row, you can see that we prompt the model to bit of turning left, and the model can crash into the first vehicle. But without the simulated data, it will not. It will still go into the lane. And yeah, since it's more common in human demonstrations. And also, the Vista is something like this. Yeah, here are more examples. Also, we can see that by introduce more diverse, by introducing more diverse action condition samples, our models can actually lead to higher visual qualities compared to the model without simulated data. Because if it doesn't see such an action condition during training, and you prompt it in inference time, the generation might crash, just completely crash without any meaningful output. Yes, and here are more visualizations. And on the left side is the ground truth video. So it's ground truth YouTube video sequence. And on the right, we prompt such video with new actions. And even if it's extremely real actions, it can still, for example, on the second row, it can still simulate the consequences reliably. Yeah, here are some human preferences. So our model is 2 times higher preference rate in both visual realism and trajectory following capabilities. And a second thing done by this work is to derive a reward after the synthesis of a video sequence. So to be so specific, we after getting such a simulated video sequence, we can use it as a input to a reward simulator, a reward estimator, and to output reward to indicate how good the action input is, right? So for any type of given action, you will simulate the video sequence and you pass it into our video to reward estimator, and it will generate a scalar indicating the quality of the action. So a low action or a negative action will lead to a low reward output. And this model is also following the philosophy of our last few chapters. It is completely trained in the simulator. So it's completely a sim to real transfer of the real video to reward model. It's trained in the simulator to compute reward given any type of video sequences utilizing the annotation of the simulator. So any type of simulator will give you a proper reward or proper signal indicate you how good the action is, right? So we utilize that as the supervision and learn a model within this simulated data, and we directly use it in inference time on real world corpus, real world scenario samples. And we can see the positive transfer across the sim to real regime. Yeah, so with the simulated data, the reward correlation is higher than previous baselines. Yeah, so in terms of applications, the first interesting we found out is that despite the word model is action conditioned, and since we trained our model in a setting that we drop out the action in some percentage during training, so it has some ability to synthesize the future outcomes without the given action input, right? So we take it as a capability as visual planning. For example, for any given video sequences, and we prompt it into the model, and the model will generate a video outcome or video imagination without requiring to input the action. And after the generation, we further convert such video sequence into a low-level trajectory as our planning trajectory. It has an extremely lightweight model. And by doing that, our model indeed surpasses many previous solid baselines. Also, this model is utilized only from view only, so it's not doing multi-view generation and it does not require multi-view input, but it surpasses multi-view baselines previous research. Yes, and the first application is actually not using the action condition capability, right? So the second application is utilizing the action condition probability and we introduce a reward guided policy selection, which means that for any scenario, we propose two different actions, and we use our model to select which action is better in this scenario, in this state. And by our model's judgment, we can obtain a much higher result compared to using any one of the single proposals. So if you always executing the first proposal or always executing the second proposals without any comparisons between them, you will result in extremely low results in planning benchmark. You compare them all the time for each state, you will achieve a higher result. And the last application is roll out your word model in several steps to achieve closed loop visual simulation. So So previous benchmarks are despite the simulation in a short horizon, it cannot roll out your model with multiple action proposals. It can only roll out your scenario with one-time planning result. But due to the long-term rollout capability of our world model, we can continuously roll out the model with more observations and with more observations into the planning method, and the planning method will further propose a new action sequence into our world model. So it can do multi-time of the world. Yeah. I may pause here for any questions with previous parts, and after that, I might introduce some of my recent thoughts on the world model regime. Yeah, so I'll pause here to get some questions.
Thank you, Jiazhi. Are there any questions about this part?
Are we gonna have questions? Okay. I have some questions.
Yeah, sure, go ahead.
For the simulation, how is it done exactly?
For simulation?
Yes, like how do you simulate a sim, like an edge case?
How do you do the rollouts, Jiazhi?
How do we do the rollout, right? So how do we roll out the model multiple times, right?
Yeah.
So once we roll out model, so once we predict the future outcome one time, we can then utilize the last few frames of predictions as the input condition for the next time rollout. So you can do that autoregressively to do the multiple times of rollout, right? You can always utilize the last prediction as the input for next time prediction.
I have a question. What do you think about the after effects? As you know, for example, in our project to learn rewards, etc., we need to observe the consequences of certain actions. For example, exact crash mode, etc. Do you think there's a way to simulate this with this model, or do we need to do more? Like, do we need to do something else to simulate the exact consequence of the action?
Yeah. So the reliable simulation or the reflective simulation can be further improved. I mean, the model is far from perfect, but it's just maybe the first work to introduce the simulated data into the training, but it's still far from perfect. And I demonstrate one scenario here where it successfully crashed into the first vehicle, right? There are a few times that it's just completely bypassed the vehicle and continue to go straight without any physical feedback. So it will now simulate the crash moment. I think it's due to the limited data scale of the simulated data. So I think we can. Currently, I'm still generating more simulated data to and add them into the co-training corpus and to encourage the reflective simulation. Yeah, but I think it's definitely worth exploring. It's not solved yet.
Well, my question is more general. Do you think it's possible to learn these kind of physical properties, physics of the world with just video models, or do we need something more?
Yeah, that's a quite hard question. So recently, I'm thinking about. So, for example, if we want to learn the physics from the videos, the first answer is yes, we can do that, but with massive or unlimited compute and data, which is not achievable. Especially for us researchers. So we can do that with video model only, but that will consume a lot of resource. But another alternative is to inject your model with some learned priors of established model. For example, there are works that supervise your video model with some 3D priors. So it supervises your video predictions with the features produced by VGGT, which is a 3D foundation model. So in that way, it actually regularize your video model feature with some 3D prior knowledge, and that will actually help improve the convergence of the learning process, and I guess it will certainly contribute to a improved physical understanding. Yeah. But is actually unstudied or on less charted scenarios, and I think it will take a lot of efforts for us to understand how much resource we need to achieve that physical simulation, right?
Thank you, Jiazhi.
Yeah, and I might continue because I'm thrilled to share some of my recent thoughts on the directions of world models. So let me look at how much slides I have. Okay, so I might be a little bit quick if the time is up. So okay, I see. Yeah. So the first thing I want to discuss is that there is a long-term debate over the type of world model we want to develop. So there are two types of researchers standing for their perspectives. So one type of researchers says that we need to develop world models that simulate video or image sequences that are basically the same thing, but simulate the visual outcomes. Right? So simulate every pixels of the future scenarios. And this is because by doing so, we can utilize a massive amount of video data that's available on the web into the pre-training. Yeah. And this is one type of researchers. But another type of researchers says that using visual outcome as the learning supervision is actually a dumb idea, because because learning to produce video sequences is compute intensive, and it's actually slow in inference time. Right. So they propose, or instead they want to develop a world model that only predict or only output a abstract feature, abstract representation instead of pixels. They are just utilize the abstract representation, intermediate representation into planning. So with that model in hand, you actually cannot simulate any visual scenarios, something like that. All you can get is a high dimensional vector. So I actually did researches on both sides a little bit, but I will confidently say that the right side is probably the wrong way to go. I don't know whether you guys are studying the world model research, but the right way is not the thing you need to try. You want to try right now, because the problem in latent world model that only predict high-dimensional features instead of videos is that you cannot verify so there's no way to semantically verify the how good your feature is learned. You cannot do any type of reasonable evaluation on these high-level abstracts. You just don't know what it generates and what it doesn't. You don't know what it's focusing on and what it's not focusing on. So there's no way. So based on the flow on the verification side, there's no way for you to clearly think about the improvement to optimize this model, because you just don't know which direction to optimize. You don't know. Yes, whether it's learning the background or the dynamics or the foreground, you just don't know. There's no idea. But with the video world model, we actually can simulate quite massive videos in inference time to see the state of this learning process. Right. If your model is bad in video sequence in temporal coherence, we can introduce some tricks or introduce some strategies to improve the temporal coherence part. If your world model is for example bad at frame transitions, you can introduce some things to overcome that challenge. So due to the gap in the verification, I think the left side might be the right way to go for any person doing the word model. Also, the fun thing is that the Dreamer series, the author of Dreamer series, that proposed Dreamer V3, which is a latent word model, he switched to doing the visual word model that produced the video sequences instead of the latent. Yeah, so I think at that point, the debate might has ended right now. So we should definitely go to the visual word model. Okay, a note is that my personal thinking is not 100% validated, so you can just take it as a reference without just completely trust it, right? And the second thing I want to say that so many papers doing driving word models, they will highlight the property of doing long-term imaginations. For example, you just you prompt your model with with 3 frames or 1 second of historical observations. It will generate 1 minute or 10. It will generate 1 minute or more than 1 minute or more than 10 minutes of future outcomes. And they say that it's a good property of the word model. Actually, it's not right because it's not what we want for a driving word model. Because for driving, we as the scenario complexity is extremely high. So if you route your model into a much longer horizon, the error just over dramatically accumulate. And you just don't know how to alleviate such error because the inference time is not controllable how the future scenario goes. Yeah, and also come with the explosive uncertainty because any time of route, you are imagining something that's uncertain, that's not observed in the input. And also for driving, we only consider the local action. We only consider the type of action you are taking at the time T instead of considering the future of, for example, 10 minutes later. We are not considering that as a human during our driving. So my opinion is that we should not focus in this part anymore. So we can forget about all the matrix evaluating the long-term imagination qualities because it's not useful. Yeah, and I may skip these 2 parts because I described it a little bit in previous parts. And to close my presentation today, I will encourage people to put efforts into the community of developing a foundation word model or developing word model for any type of intelligent agent. Because the word model is highly capable. If you think it just as an abstraction of the environment, it actually can serve what the environment can do. Right, because what the environment can do, in theory, the word model, the abstraction of the word model can also do the same thing. So based on that, the word model has much more capabilities. For example, it can, using model predict control, it can refine the action by any given pre-trained model. It can adjust the actions to a desired way. And with RL fine-tuning, we can improve the policy, improve the pre-trained policy with the signals produced by the word model. And the word model, as it generates synthesis data, it actually can be a data engine to augment the data corpus during your pre-training. And further, the word model can be an evaluator because it's hard to do evaluation for driving in realistic world, right? So for any of our researchers, we understand that because we don't have a real car that can run all of our ideas in physical world. But in word model, we don't have that worry because if your car crash in the word model, it's not causing any negative effect in the physical world. So no worries on the evaluation. And a good word model can also be a policy evaluator. Yeah, so I think there are a way to go to develop a valid and applicable word model to facilitate the intelligence agents, including driving and robotics. And I think that's exciting.
Thank you,
Yeah,
Jiazhi.
that's all for my presentation. Thank you.